Hello everybody and welcome. We are group number 32 on behalf of State LA's Baja SAE team, and our project is the four-wheel drive integration. Our faculty advisor is Dr. Christopher Bachman, and our group members include myself, Aaron Corona, Chris Escobar, Ezechiel Lucien, Maung 2, Brian Torres, Britney Tran, and Rafael Zamarron-Brito. Going over the agenda for today, we will start with an introduction and background of our project. We will go over our project requirements, as well as our technical progress, diving into the chain drive, the differential, the wheel hub, the brakes, front suspension, shocks, and the driver ergonomics. So for our project background, our team objective is to primarily design a four-wheel drive Baja vehicle. A little bit of background on this. Baja SAE is a collegiate design competition where students must design and manufacture a single-seat off-road vehicle. The competition rules for the 2022 year now require all cars to be four-wheel drive. Going into our vehicle requirements, the first requirement is that all four wheels shall be powered by the engine as established by the competition requirements. We also want the vehicle to comply with all rules based by the Baja SAE competition. The vehicle shall have no failures over a 6-hour endurance run, as established by the competition's running time. The vehicle shall have acceleration times within 5% of the two-wheel drive vehicle, as established by the team's goals. And the vehicle shall place higher in competition in the dynamic events, including hill climb and maneuverability, also established by the team goals. Now for the team breakdown. I myself am in charge of the front suspension, which includes the geometry and the kinematic analysis, as well as designing the CADs and doing the stress analysis. Britney is in charge of the front differential, which includes the differential placement, as well as mounting CAD and the analysis. Chris is in charge of the shock analysis, which includes shock selection and tuning, as well as establishing a quarter car model and a half car model. Rafael is in charge of the steering wheel and the front hubs, which includes CAD designs, as well as analysis and fatigue analysis. Maung is in charge of the chain drive, and he will be responsible for the sprocket and the chain selection, as well as the tensioner design and analysis. Brian is in charge of driver ergonomics, which involves the seat placement and the steering wheel placement, as well as the seat CAD. And Ezechiel is in charge of the brake system, where he will be handling the pedal design, as well as the master cylinder and brake caliper selection. And now I will be passing it on to Maung, who will talk about his chain drive.
Hello everyone, I am Maung and I am in charge of implementing the chain drive. From the figure in this slide, we can see that the chain stretches from the front to the rear of the vehicle and is engaged with sprockets at each ends. The tensioners indicated in yellow help guide the chain beneath the driver's seat and help maintain proper chain tension. To select the chain, it is important to consider the listed horsepower, RPM, and gear ratios because they help decide the required strength of the chain in operation. Therefore, we must select a chain that can withstand 9 horsepower and a sprocket speed of 117 RPM. To ensure both front and rear tires rotate the same rate, the chain gear ratio must be 1.03 to 1 because the tire sizes are not the same. There are several types of chains, but we have selected roller chains due to its versatile use, including transmission of mechanical power. Roller chain sizes vary by its pitches, and the chains are commonly made by carbon steel. If we turn our attention to Table 1, preliminary chain size of 80 is initially selected by the given information of engine horsepower and RPM of sprocket. Here, working load represents the chain tension, and we can see that it's within the range of allowable working load. Ultimate tensile strength tells us the threshold of when the material will begin permanently to form, and weight is considered because we want to reduce the weight of the vehicle as much as possible. In addition, the size of the front and rear sprockets must not interfere with other subcomponents in the nose and rear of the car. From Table 1, we can see that chain 80 is a heavy chain, and the sprocket size is larger than 6 inches. Therefore, chain 60 is analyzed to explore for lighter options. Chain 60 will be an ideal selection for our system, since it is much lighter chain and its sprocket size is much smaller. However, Allowable working load is calculated in consideration of a chain service life of 15,000 hours. Since the vehicle only needs to withstand a 6-hour endurance race, we explored a lighter chain. For chain 50 with a sprocket teeth of 26 and 27, chain tension is above the allowable working load by about 400 pounds of force. However, this is under the consideration of again 15,000 service hours, and we can also increase the chain service life by preloading, which is same as strain hardening, a manufacturing method to increase material strength. We did not explore any other lighter chains because working load calculated for any other lighter chains are 50% or more of the material ultimate tensile strength. This is unacceptable because the chain will either permanently deform or break after one cycle. Here we have explored views of the tensioners. The rollers on these tensioners are 53mm skateboard wheels, and they must be shaved down to create a channel for chain to travel through. The chain tensioner can be adjusted slightly by turning the nut down. The plates can be manufactured using the mill and the drill press. From this point forward, we will be looking into a few analyses of the rear tensioner only since similar results and design revisions are received and taken for the front tensioner. Here we have our FEA static stress analysis of rear tensioners. They are designed to support the force supplied by the chain deflection, and the forces are listed on the table. The top load indicates the forces acted by the top chain deflection, and the bottom load by the bottom chain deflection. Let's turn our attention to rear tensioner static stress analysis. From the figure with the Vermeer stress plot, we can see that there are stresses that are above the yield strength, indicating that the structure would deform under these static loadings. This is particularly due to different directional high loads that are causing shear and bending stress at the rectangular beam and at weldment sites. It is clear to see that this design will not satisfy the minimum factor of safety of 3.0. Therefore, a new design is considered. For the next design, we take advantage of the rectangular beam in front to support the previous tensioner. This support will help some of the adjacent forces from the total load. Even with this additional support, the minimum factor of safety was less than 1. There were several changes that were considered, such as increasing the plate thickness and creating more surface contact with the beams. However, all of these design changes made little to no difference to the stresses. A particular change that was implemented that made a significant impact is changing the thickness of the tubings. After increasing the thickness to 0.15 inches, Vermeer stresses were well below the yield strength, and the minimum factor of safety is approximately 2.0. Areas of which it fails factor of safety requirement of 3.0 are at weldment sites. At those locations, the stresses are high due to sharp discontinuity, and as a result, it gives high stresses, and it is simply a computational error. Therefore, those stresses at those sites are neglected, and since factor of safety of 3.0 are found everywhere else, it is safe to conclude that this design will pass the static loading test. Now, I will be handing off to Britney to talk about the differential.
Thank you, Maung. So my role on the team is the power delivery from the front differential to the front two wheels, and this requires me to complete 3 separate tasks. My first task is to determine the location of the front differential, my second task is to lengthen the CV axle, and my third and final task is to house all spinning members of the front drivetrain. So to start off, I place the front differential right in the center of the car at 7.5 inches as shown in the green arrows on the left figure. And then I put the differential as low as possible to the ground to fit the sprocket of 5.18 inches in diameter so that it is 4.6 inches from the bottom member, as shown in the right figure. And this is to keep the sprocket in line and as low as possible to the ground so that the CV axles can have the maximum range of motion. For the same reasons, I placed it 5.53 inches from the back end of the nose. Now that we determined the location of the front differentials, we can determine ways to mount the differential at that location. Last semester, we investigated 5 different designs of the mounting members. However, 2 designs were eliminated due to their complex manufacturing processes. So the top 3 designs shown here went on to FEA analysis in SOLIDWORKS to determine the factor of safety values. For case study 1, we use a tension of 1,300 pound force at an 83-degree angle. The factor of safety for this case study yielded to be 0.19, 0.65, and 1.8 for designs 3, 4, and 5 respectively, and this is shown on the table to the left. However, halfway through the semester, the tension increased to 1,884 pound force at an 85-degree angle. But instead of rerunning these studies, we know that factor of safety is directly proportional to the force applied. So we can just multiply the factor of safety by a proportionality constant instead of rerunning the studies to obtain the new factor of safety. Also, before rerunning these studies, we want to ignore the areas where stress concentrations are reportedly higher than the reality as shown in SOLIDWORKS. So these locations are right here, here, and here, or in other designs here and here. And that's because at these areas, they have sharp contours, and per stress concentration theories, these areas will have high stresses, but we know we will fillet and chamfer these areas because we are going to weld them, so we can ignore them. So the new corrective factor of safety values are 0.84, 3.72, and 3.17 for designs 3, 4, and 5 respectively. These factor of safety values were then used in the secondary PUG matrix to determine the finalized design to be integrated into the car. These 3 designs were judged on their factor of safety, integration support, and material usage. Factor of safety was given the highest weight of 3 because it is a requirement of the drivetrain components to have a factor of safety of 3 or greater. So we wanted to ensure that these designs were safe. So with that being said, design 5 earned the highest amount of points at 4 points total. So it will go on to the integration and manufacturing phase for the 2021 season. And that concludes my first task. For my second task, I was asked to lengthen the CV axle by 12.75 inches. And this is so that the axle can reach to the front differential to the front 2 wheels. The way I did this was split the axle in half as shown here, connect it with the middle rod, and then I put a sleeve over it. The sleeve is made from 4130 steel and the axle material is unknown. This will later come to be important as we analyze the factor of safety values. The factor of safety values for the axle was determined to be 1.2 and for the sleeve to be 2.7. As stated previously, all drivetrain components should have a factor of safety of 3 or greater. As shown clearly, this does not meet the requirement. And to verify these numbers, we did hand calculations shown at the bottom 2 tables, which show that they nearly match SOLIDWORKS' values so that we can determine that this model was modeled to a high degree of accuracy. So in the previous case study, the CV axle did not meet our requirement. So to increase the factor of safety to 3, we can increase the outer radius of the sleeve to 0.5625 inches. And that is because the shear stress is directly proportional to the radius. If I increase the radius, the shear stress decreases such that the factor of safety increases to 3.2 as shown in the figure below. And it now meets our requirements. Again, the 2 tables below validate the software's solutions as it nearly matches our own hand calculations. But it is still important to point out that the factor of safety of the axle is 1.22 and does not meet our requirement since it is below 3. However, we can disregard that factor of safety value, because in a market survey that we saw and conducted, we saw that vehicles that use the exact same axle supported torque values up to 3,500 pound-inch. But for our applications, we only needed to support 2,625 pound-inch of torque. So it is more than sufficient for our applications. Nevertheless, the axle can still be extended safely by 12.75 inches with a factor safety of 3.2. So this concludes my second task. For my third and final task, I was asked to house all spinning parts of the front drivetrain. So this includes the chain, sprocket, and front differential. The way I did this was simply molding a 1/8 inch aluminum plate over these spinning members. And that is because I wanted to have the smallest amount or take up the smallest amount of space in the nose, but still give it enough clearance so that they can spin freely. I then cut 2 holes here so that the chain can enter and exit. So the way the housing will work is that there are 2 separate plates This plate will be welded onto this plate, and these areas will be bolted down onto the differential mounting members themselves. So with that, it concludes the ending of my third task. Now I will pass it on to Rafael to talk about the wheel hubs.
Our design parameters entail properly utilizing the four-wheel drive, so the front hub needs to accommodate a CV boot and a half shaft. Here we see on the right side of our screen, we see 4 design concepts, but acknowledge that 3.2 is a rendition of version 3 after the first semester, where we adjusted for a offset so that the wheels can meet the Ackerman angle on the steering. Here at the bottom right, we see a side view of how the hub will look near the vehicle. Here we have our concept selections for the front hub. There are 3 versions, version 1, 2, and 3. Here is our trade study to show which one we're going to choose. And here the green box outline indicates the final design, which is version 3. All the designs, only 2 of the designs were able to meet the minimum factor of safety requirement. Version 1 did not meet it. It was also one of the heaviest designed ones, but still it was one of the concepts we had to consider. And below we have some FEA simulation resultants that we got from it. And here we have a front hub update. After integrating the first CAD into the vehicle CAD, we realized that the hub did not have the proper offset. So we increased the base before the spindle to push the wheels further out so that there is no interference with the measurements we desire. For this semester's goal, we conducted hand calculations and fatigue analysis simulations. For hand calculations, we conducted a torque analysis on the internal splines of the front hub. So we see here that we applied 5,040 inches-pound torque applied to the splines. We were able to receive a factor of safety of about 1.01. Even though this is a factor of safety of 1, which in most cases would be something that's not passable, this is what we consider a worst case scenario, since this torque is actually the max capacity of the gearbox, and what we would consider, and it's in a situation where all the torque is being applied to one wheel, since it's a four-wheel drive vehicle, and all the weight is being applied to that same wheel. So it is what we consider a worst case scenario, but something that should never be neglected. So it does pass. For fatigue analysis, we conducted simulations through SolidWorks on both the steering wheel and the front hub, but currently we are only able to obtain results for the steering wheel. Still trying to attempt to obtain results for the front hub. But here for the steering wheel, we actually get a result at 100,000 cycles. We get a failure point about 94,000, which is good to know. So this is something to consider for designs in the future, so we know how many cycles we can consider in fatigue and stuff like that.
Thank you. For the brake system, the first thing we'll talk about is the brake requirements. And as you can see, there's only one requirement, that all the wheels will lock. Next, we move to design concepts. And there are 3 parts that we'll focus on. That is the brake pedal, master cylinders, rear, and front calipers. And as you can see, for all these parts, there are 3 options to select from. And now we'll focus on the brake pedal. And as you can see, version 3 was selected. And this is because, regardless of criteria, from price all the way down to factor of safety, version 3 was the best option, regardless of criteria, making us have to select version 3. But now, when we look at the factor of safety, what we see is there's a 450 pounds being applied to give us that factor of safety of 1.9. And since 450 pounds is not what normally is applied by 1 foot, this would mean that our factor of safety of 1.9 is actually a lot higher. And to make sure we have a durable, light pedal, the material we used is aluminum, as you can see here. Now let's focus on the master cylinder, which we have two. And this is because we use the GS compact remote. And it was selected because of the bore size, the stroke, and the reliability. And when I say reliability, I'm talking about if it's been used before by us, and if it's designed for the purpose we want to use it for. And in the case of the Cartmaster, none of those criteria matched, and that's why it has this value. And for the Tandem, it had both of those, and that's why it has a 5. While for the GS, only one of those criteria was met, and that is that it is designed for the purpose we wanted to use it. And some key things to know about our master cylinder is that it was designed for 1400 psi, but it's only tested for 12. Now let's take a look at our calipers, starting with our rear caliper, which we have two, and this is because last year was a 2-wheel drive design. Now we're dealing with a 4-wheel drive, which required us to move our rotor from its previous position to a new position, which causes us, as stated before, to have two rear calipers. And because of this change, the PS1 was selected as a rear caliper. And this was based off the price, the bore, and the size of the PS1. Now, let's take a look at our front caliper, which the GP200 was selected. And this was based off the criteria of the mass, the mount side, and the size. And one convenient thing that happened when selecting these is that the inlets are actually the same. Now let's take a look at our efficiency, which is when we are applying 100 pounds to the pedal. Our front efficiency is 2.55 and our rear is 2.29. And for our ratio, which normally should be 70, we have 53, and this is because we wanted oversteering, and this would help us hit our corners a little bit better, since some of our steering was a little bit tighter than what we actually wanted. And to give the driver more control, if this setup didn't work as well, we could always install a proportional valve to give us slight more control over the ratio, which gives the driver more control of the car. Now let's take a look at our housing, starting with our master cylinder housing. We have two of them, and their factor of safety is 1.7, and this is when a full load is being applied to the to the housing from the pedal. But since there are two housings, the load will never be the full load, which means our factor of safety would be actually higher. And now we move to our pedal housing, which had a factor of safety of 6.6, and both the materials were made out of steel so they can be directly welded to the material, to the frame of the vehicle. Some other achievements are the improved braking sheet, which uses equations like this to find torques, forces, and pressures at any point in the braking process, which gives us more accurate data to help us get a better braking ratio. Also, the energy requirement for braking was also calculated, so we could have a better understanding of the heating that would happen in the rotors. And the other achievement that is currently being worked on is the nose model, which is basically we're going to build the nose and everything in it. And this will help us have a better understanding of the building process, which will improve our next design. Now we move to front suspension, where Aaron will take over.
Thank you, Ezechiel. And now for the front suspension. As we rolled into this new semester, it became increasingly obvious that the nose of the vehicle was going to be too small to properly package everything that needed to be included. This includes the front differential, the sprocket, the rack and pinion housing, the brake and throttle pedal, and the driver's feet. So due to these constraints, the suspension geometry needed to change in order to accommodate a wider nose. We were able to redesign the suspension geometry and the kinematics using VSUSP, and we were able to maintain the exact same values from the previous iterations. All of the design concepts were redimensioned in order to accommodate the new suspension. This includes the kingpin, the lower control arm, also known as the A-arm, and the upper control arm. As we can see here, we have the bottom arm concepts, which are all made by 1-inch diameter by 0.049 thickness, 4130 steel tubing. The top arm concepts, which are all made from 1-inch 065 tubing, and the kingpin concepts, which are all planned to be machined out of 6061 T6 aluminum. To help us in select our final design, we ran each concept through each iteration through a variety of different load cases using FEA, and then used trade studies to help us pick which design was going to work best for us. As for the top arm, you can see that we analyzed it. One of the load cases that we analyzed it in was the vertical direction, such as when the car hits a bump. For the bottom arm, we analyzed it in a longitude. One of the ways we analyzed it was in a longitudinal direction, such as when the car experiences a frontal impact. And for the kingpin, we analyzed it in the longitudinal direction, again, such as when the car feels a frontal impact. On the right, you can see the trade studies where we compared each iteration across each other using a variety of factors, including the manufacturability of the component, the factor of safety, the cost, and the mass of the component. And here we can see a finalized view of the front suspension. Some of the things to note include the shock placement. As you can see, the shock is placed onto the upper control arm of the front suspension, whereas previous years it was placed onto the lower control arm. This was done primarily to make space for the CV axles that you can see coming from the differential to the kingpin that allows the front wheels to be driven. And with that, I will be passing on to Chris so he can discuss his shocks.
Thank you, Aaron. Analysis on which type of shock would form best was needed with the new car designs, particularly the changes done on the front of the car to make the necessary accommodations, as Aaron previously mentioned, for the new four-wheel drive rule. Proper shock packaging is vital for vehicles, especially when it comes to competitions, in order to increase the overall off-road speed by limiting the chassis movement and providing the most stable and controllable ride for the driver. On the left here is an example of an air shock, a single spring coilover, and a dual rate coilover shock. To analyze the performance of linear and progressive shocks, a quarter car model simulation was made for both in MATLAB. In the figure here, we have a schematic of a quarter car suspension, where M2 represents the sprung mass, which is a corner mass that is supported by the suspension. M1 is the unsprung corner mass, which consists of the summation of the mass of tire and wheel assembly, the hub, kingpin, calipers, axle, half the mass of the spring and shock, basically the addition of any mass that is not supported by the suspension. K1 and K2 are the spring rates of the tire and the shock spring rate respectively, and C is the shock damping rate. In this figure shown here, X2 represents the vertical displacement of the chassis center of mass, X1 represents the vertical displacement of the wheel center of mass, and Yn represents the vertical displacement of the road at the wheel's point of contact. Further analyzing the quarter car suspension schematic, which was seen in the previous slide, free body diagrams were made for both sprung and unsprung masses. Applying Newton's second law of motion to each free body diagram, The equations of motion for this 2 degree of freedom system are then found as those represented by equation 1 and 2. These equations were used in the MATLAB quarter car script so that the acceleration, velocity, position, and forces of both sprung and unsprung masses could be obtained and used for analysis. In addition to the equations of motion, there were other parameters that needed to be taken into account for the quarter car simulation, such as the motion ratio, which is a ratio of the shock displacement to the wheel displacement. The motion ratio is also directly related to the ratio of the lengths between the pivot point of the arm on the chassis tabs to the shock and the wheel mounting points. To obtain the most precise motion ratio, the angle placement of the shock must also be considered from the vertical, as shown in the figure to the right. Shock extended length is also another factor that needs to be considered, because it must be larger than the distance between the shock mounting points on the chassis and the arm tabs when the car is at ride height. Droop, again, another important factor to consider when looking at shock lengths, since ideally there needs to be roughly about 40% of the shock travel compressed at ride height for down travel, which means that that amount of shock travel is in the shock body, which reduces the shock extended length. The following set of figures is an example of the MATLAB outputs produced by both single and dual spring quarter car model simulations. The outputs of each code have been implemented in the same plots for comparison. This is an example of the rear end hitting a ramp with height of 6 inches. In the legend, the acronym DS stands for dual spring, and SS is the single spring data. The single spring rate is 32 pounds per inch. Meanwhile, the dual spring setup is composed of a 19 pound per inch primary spring over 45 pounds per inch secondary spring. The combination of these springs is found by combining the springs in series. To do this, both spring rates are multiplied and divided by the summation of the spring rates. The end result is a 32 pound per inch spring rate when both springs are active. Here we have an exploded view of the two plots from the previous slide. Looking at the position versus time plot on the left, if we follow the sprung mass positions for the linear and progressive setups, it can be seen how the dual spring system, which is represented by the blue line, settles a little faster than the single spring system, which is represented by the yellow line in this scenario. Now, observing the force versus time graph on the right, the max force on the sprung masses occurs nearly at the same time in the simulations. There is 29.55 pounds force more on the sprung mass with the single spring setup than there is with the dual spring system, as it can be seen by the represented points. Analyzing the results of several road profiles for both front and rear end simulations, Table 1 and Table 2 were made to assist with determining which would be the best shock option. As it can be seen, for both front and rear end simulations, the dual spring system had the lowest force and displacements of the sprung and unsprung masses compared to those recorded by the linear spring script. This led to the choosing of the dual rate progressive system over the single spring rate linear one. From there, the next step was to choose which shock model to go with. Another decision matrix was made, the one seen on the right, where we compared 4 different shocks based off of price, weight, travel length, adjustability, and extended length, and rated them on a scale of 1 to 5, where 5 was the best option. After this was done, it was clear that our option would be the Genesis G6 shock. And that concludes my shock subsection. I will now pass it on to my teammate Brian, where he will discuss about his driver ergonomics study.
Hello everyone, my name is Brian Torres and I will be going over the cockpit ergonomics. So on the slide we'll have a quick overview of the factors considered and the manufacturing methods that we decided to go with had we constructed our components. So the factors considered are first and foremost safety. We want to ensure that no matter what driving conditions the driver encounters, we want to make sure that first and foremost their safety is considered and a priority. Secondly, system integration. So with the addition of a four-wheel drive system and new components, just to name the chain drive and the differential, we've had to consider various measurements in order to ensure an optimal system integration. Thirdly, we've also had to base our designs on quantitative data as opposed to qualitative data. So as you will see later in the presentation, I'll go over some of the information that consists of the purely quantitative data, which we based our design decisions off of. Lastly, our manufacturing methods. So had we constructed our materials, we would have used a 3D printed mold. We would lay over fiberglass over the 3D printed mold. Then lastly, we would use vacuum resin infusion for the carbon fiber on the fiberglass mold. Continuing on, so on this slide here, we have 4 different views of the 2 ergonomic components which we had designed in SOLIDWORKS. So we have a front view, left side view, top view, and an isometric view of the seat and the steering wheel. Most notably, I'd like to point out that the seat was designed to fit the average driver. So we included measurements such as the width of their legs, the width of their back, and the height of their shoulders from the hip. And for this steering wheel, we had included in the design an aluminum core, which would add strength to the overall steering wheel, and we would also 3D print the handles so that they conform best to the driver's hands. So moving on to the data collection and the analysis summary. So a questionnaire asking for prospective driver body dimensions was sent out to the prospective drivers, and we would use these measurements to determine one critical component, which is the center of mass of the driver. In previous years in the Baja competition, this was actually not accounted for. And with the integration of a 4-wheel drive system, we will have the addition of multiple new components, each adding to the overall vehicle center of mass. And so therefore, calculating the center of mass approximately for the driver would help us determine the handling characteristics of the vehicle in the long run. So on the right, we have a table including the analysis summary, which we obtained. Using a research paper, we were able to determine the approximate weight percent of each of the body parts, namely the head and the neck, the trunk, the upper arms, the forearms, the hands, the thighs, the lower legs, and the foot. So, using the measurements which we obtained, we determined that the center of mass in this instance would be approximately 5 inches to the driver's hip and 23.3 inches off the ground. That's including the vehicle height. So continuing with the analysis summary, on this slide here we have the results of the rapid upper limb assessment, so RULA for short, determined a ground score of 6. Now in this instance, RULA dictates that a ground score of 6 means that it's medium risk and suggested to change. However, we consider this acceptable for our needs because the driver will be in the vehicle for no more than 2 to 4 hours, after which we expect to swap drivers. So in this case, it meets our requirements. As mentioned previously from the table, we obtained the driver body measurements and we were able to determine the center of mass on a 2D plane. Of course, this is just an estimate. So for a driver, an average driver, which is about 5 foot 9 inches and approximately 170 pounds, the center of mass was determined to be 5 inches forward from the hip and 23.3 inches off the ground. And if you'll take a look to the right, we have the table visualized. So you'll see that the y-axis extending directly up from the hip, and the x-axis denoted by the most horizontal line on the bottom, which indicates the ground. We were able to approximately come up with some angles and some measurements which would comply with our requirements. And as you will see in the next slide, we go into detail with this, where we determine which drivers would fit in the vehicle and ultimately which drivers wouldn't. And this would allow us to justify our conclusions for the best fit drivers. So now going into our final analysis summary slide, we have here to the image on the right, it's essentially a summary of the previous 2 slides, which consisted of the driver measurements and ultimately how they would fit in the vehicle. So if you remember on the previous slide, it was a 2D sketch. So here we have the combination of the 2D sketch, but also this time a 3D human model, which we measured to the average driver height, of course eliminating the most extremes, meaning drivers that were too tall, and in this case we didn't have any drivers which were too short. So going into the summary, we have targeted body angles which were obtained through research paper done in this area of suggested body angles for a driver within a vehicle. So we have elbow angle of 90 to 170 degrees, a hip angle of 80 to 120, knee of 100 to 150, and an ankle angle of 80 to 120. So combining our 2D sketch and our 3D human model, we were able to mock up what a human would actually look like. In this case, this model is about 5 foot 6 inches tall. So a driver that's about 5 feet 6 inches tall would look something similar to this. Now this model is of great value to us because it essentially reaffirms our measurements, which were taken in the 2D plane and also in the table. Now, assuming that they weigh about 370 pounds, we can also determine where their approximate center mass would be. So the measured results from this 3D model here, we have an elbow angle of about 115 degrees, a hip angle of 81 degrees, and a knee angle of 128 degrees, an ankle angle of 81 degrees. Again, the importance of this being that a 3D model ensures us that when construction of the vehicle is complete, our average drivers will be able to fit inside the vehicle and therefore perform their best during the competition. Now that we have concluded the driver ergonomics section, next Aaron will be going over the summary of our project. Thank you.
Now, to provide a quick summary, as you can see, the initial goals for this year were to design, build, and test a four-wheel drive Baja style vehicle. However, this did not exactly go as planned. Some of the issues along the way were obviously the lack of lab access, and this obviously did not allow for manufacturing, as this does not include just our own manufacturing, but the manufacturing of the entire Baja team, including the frame, the rear suspension, other components that were not accounted for by just our senior design team. Another issue, a vast issue that we had along the way, was the packaging constraints within the nose of the vehicle that prompted redesigns for various members, including myself on the front suspension, Britney with the differential, Rafael with the hubs, and even Brian with some of his ergonomic analysis. Despite that, we still achieved some final results. We achieved finalized designs for all subsections of the vehicle, which are completed, and we took the time to do a little further analysis on these components, and we assure that they are ready to be manufactured. On the right here, we can see some of the components that the team has worked on, including the steering wheel placement, the seat, the front suspension, the differential, the chain drive, and of course the brakes and the hubs. And on the bottom we can see the overall 2021 Baja SAE vehicle as designed by us and the rest of the team at State LA. Thank you.